Hello guys. So I'm Russell Guadalupe and I'm going to discuss some examples and exercises about sequences of real numbers and their convergence. So first, let's recall what we have learned from the lesson last time about the sequences of real numbers. So we say that an infinite sequence A sub n of real numbers is convergent if we can find a real number L such that for any positive epsilon, there exists a natural number capital N such that the absolute value of A sub n minus L is less than epsilon for any n greater than capital N. In this case, we write the limit as follows. The limit of A sub n as n goes to infinity is equal to L. And then we say that the given sequence is divergent if we cannot find such number L that satisfies the convergence condition above. Then we say that the sequence is increasing if for any natural numbers m and n, with n larger than m, we have A sub m is at most A sub n. And then we also have an analog definitions for a decreasing sequence, a strictly increasing sequence, and strictly decreasing sequence. We say that a sequence is monotone if it's either increasing or decreasing. And then we say that an infinite sequence is bounded above if we can find a real number m, such that for any natural number n, the n term A sub m is always at most m. And we also have an analog definition for a bounded below sequence. And finally, we say that an infinite sequence is bounded if it's both bounded below and bounded above. Then you also have learned the following squeeze theorem for sequences, which states that if we have three sequences, A sub n, B sub n, and C sub n, such that for some natural number k and real number L, we have the following inequality, which says that B sub n is always between A sub n and C sub n for all natural numbers n greater than or equal to k, and the limits of A sub n and C sub n exist and are both equal to L as n goes to infinity, then the limit of the middle sequence B sub n also approaches to L as n goes to infinity. The summary remarks. An increasing sequence is bounded below by its first term, and a decreasing sequence is bounded above by its first term. And then you also have learned the following important result known as the monotone convergence theorem, which says that if the sequence of real numbers is monotone and bounded, then it is convergent. So we use these two remarks as well as the monotone convergence theorem to establish the convergence or divergence of a sequence of real numbers. So we're going to score the following exercises here. So I encourage you to please pause this video and try to solve these problems as many as you can. Okay, so let's now proceed to our first example. Let's prove using the definition that the sequence given by n over n plus 1 from 1 to infinity converges to 1. So let's first show our method of solution. So we let epsilon to be positive and we take capital N to be 1 over e. We will explain later why we take such value of capital N. Then setting A sub n to be n over n plus 1 and L to be 1, we see that for all n greater than capital N, the absolute value of A sub n minus L is equal to the absolute value of n over n plus 1 minus 1, which is equal to 1 over n plus 1. And then this fraction here is actually less than 1 over n due to the fact that 1 over n plus 1 has denominator n plus 1, which is greater than the denominator n of 1 plus n. So in this case, the fraction 1 over n plus 1 is smaller than 1 over n. And therefore, using the following inequality here, n greater than big N, we see that 1 over n is in turn less than 1 over capital N, which is equal to e. The reason why we choose capital N as 1 over e is that we need to somehow uh, simplify the given expression, absolute value of a sub n minus L, and then we have to try to make it less than epsilon. Okay? So hence, by definition, we see that the given sequence n over n plus 1 from n equals 1 to infinity converges to 1. Okay, so let's now proceed to our next example. Let's determine whether the sequence 3n minus the square root of 9n squared minus 4n from n equals 1 to infinity is convergent or divergent. So first, let's define the function f of x equals 3x minus the square root of 9x squared minus 4x on 1 to infinity. Then we have the following. Let's compute the limit of f of x as x goes to positive infinity. And then as you can see here, the limit of 3x as x goes to positive infinity goes to infinity, and the limit of the square root of 9x squared minus 4x as x goes to positive infinity also goes to positive infinity as well. So we have an indeterminate form of infinity minus infinity. To find the limit of the given function with this indeterminate form, we have to rationalize the numerator. So in this case, we rationalize f of x as follows. We multiply both numerator and denominator by 3x plus the square root of 9x squared minus 4x. And then we simplify it to giving the limit of 9x squared minus quantity 9x squared minus 4x all over 3x plus the square root of 9x squared minus 4x. As you can see here, we actually applied the difference of two squares to our numerator. And then we have then the limit of 4x all over 3x plus the square root of 9x squared minus 4x as x goes to infinity. And then again, we multiply both numerator and denominator by 1 over x. So this simplifies to the limit of 4 over 3 plus the square root of 9 minus 4x, 4 over x rather. So as x goes to infinity. So as x goes to infinity, 4 over x will go to 0. So therefore, the limit here approaches to 4 over the square root of 9 plus 3, which gives us 2/3. And because f of n is equal to 3n minus the square root of 9n squared minus 4n for all positive integers n, we have the limit of the n term of the given sequence as n goes to infinity is equal to 2/3. So therefore, the given sequence 3n minus the square root of 9n squared minus 4n from 1 to infinity is convergent with limit 2/3. So let's have another example here. Let's determine whether the sequence square root of n all over ln n from 3 to infinity is convergent or divergent. So again, just like in a previous example, we define the function f of x equals the square root of x over ln x on 3 to infinity. Applying L'Hopital's rule, we have the limit of f of x as x goes to positive infinity is equal to this. As you can see here, the limit of the numerator and denominator both tend to positive infinity. So we can apply L'Hopital's rule. So in this case, we have to differentiate both numerator and denominator here. So this gives us the limit of 1 over 2 square root of x all over 1 over x. And we can simplify it to become the limit of x over 2 square root of x as x goes to infinity, which can be written as 1/2 times the limit of square root of x as x goes to infinity. As you can see here, if x grows large, so does square root of x. So therefore, the limit here becomes positive infinity. And then again, because f of n equals the square root of n over ln n for all positive integers n greater than or equal to 3, we see that the limit of the n term here, our sequence, goes to positive infinity. So therefore, the sequence square root of n over ln n from n equals 3 to infinity is diversion. Okay, so let's have another example here. Let's determine whether the sequence sine n plus cosine n all over n squared from 1 to infinity converges or diverges. The first, let's have the following observation. We have for all integers n greater than or equal to 1, sine n is always between -1 and 1 inclusive, as well as cosine n between -1 and -1 inclusive as well. So that sine n plus cosine n will be bounded below by -2 and bounded above by 2. So in this case, sine n plus cosine n all over n squared will be between -2 over n squared and 2 over n squared for all positive integers n. Since the limit of -2 over n squared as n goes to infinity is equal to 0, and the limit of 2 over n squared as n goes to positive infinity equals 0 as well, applying the squeeze theorem, we deduce that the limit of the middle sequence here, in this case, sine n plus cosine n all over n squared as n goes to positive infinity equals 0. Hence, we conclude that the given sequence sine n plus cosine n all over n squared from n equals 1 to infinity converges to 0. So let's now prove the following statement, that if the sequence absolute value of a sub n converges to 0, then the sequence a sub n converges to 0 as well. So observe that for all integers n, we have the following inequality here, which says that a sub n is bounded below by the negative of the absolute value of a sub n and bounded above by the absolute value of a sub n. Because the sequence absolute value of a sub n converges to 0, we know that the limit of the absolute value of a sub n as n goes to positive infinity is 0, and the limit of the negative of the absolute value of a sub n as n goes to positive infinity, which can be written as the negative of the limit of the absolute value of a sub n as n goes to positive infinity, which is actually equal to 0 as well. So hence, by the squeeze theorem, we see that the limit of the middle sequence here, in this case, the limit of a sub n as n goes to infinity equals 0. So therefore, a sub n converges to 0 whenever the absolute value of a sub n converges to 0 as well. So let's now proceed to our next example, which asks for whether the sequence n over n squared plus 2 from n equals 2 to infinity is increasing or decreasing. So first, let's define f of x equals x over x squared plus 2, which is differentiable on 2 to positive infinity. As you can see here, x squared over 2 doesn't have any root on this interval, so therefore this is differentiable. Then, computing the derivative f prime of x using the quotient rule, we have x squared plus 2 times the derivative 1 of x minus x times the derivative 2x of x squared plus 2. And then we divide everything by the square of x squared plus 2. And then simplifying, we get the numerator of 2 minus x squared all over x squared plus 2. As you can see here, for all x greater than or equal to 2, 2 minus x squared is less than 0. So in this case, f prime of x is less than 0 as well. Take note that x squared plus 2 is always positive for all x greater than or equal to 2. So therefore, f prime of x is less than 0. So therefore, f is decreasing on the interval 2 to positive infinity, and hence the given sequence is decreasing as well. So let's now proceed to our last example, which asks for considering the sequence given by n factorial all over the product of 1, 3, and so on until 2n plus 1 from 1 to positive infinity. So first, let's determine whether the given sequence is increasing or decreasing. So first, let's define a sub n to be n factorial over the product of 1, 3, and so on until 2n plus 1, which is positive for all positive integers n. Then, for all n greater than or equal to 1, we compute the ratio of the n plus 1 term with the n term. So which amounts to multiplying a sub n plus 1 by the reciprocal of a sub n. So as you can see, a sub n plus 1 can be written in this way. We just have to replace n by n plus 1. So this gives us n plus 1 factorial all over 1 times 3 times and so on until 2n plus 3. Take note that for our for, to make our computations easier, we have to make 2n plus 1 appear in the product here on the numerator or on the denominator of a sub n plus 1. And then we multiply it by the reciprocal of a sub n, which is given by 1 times 3 times until 2n plus 1 all over n factorial. And then as you can see, all the factors will cancel out except n plus 1 and 2n plus 3. And then as you can see here, 2n plus 3 is always greater than 2n plus 2. So therefore, the fraction n plus 1 over 2n plus 3 is less than n plus 1 all over 2n plus 2. And therefore, this is actually equal to 1/2, which is obviously less than 1. So as you can see here, guys, that an plus 1 over an, which is equal to n plus 1 all over 2n plus 3 is less than 1. So this means that for all n greater than or equal to 1, an plus 1 is always less than a sub n. So hence, the given sequence here is strictly decreasing. So let's now consider the same sequence and show that it is bounded. So for our proof, so the terms of the sequence are positive. So hence it is bounded below by 0. But we have shown from number 1 that the sequence is decreasing, and thus using our second remark, it is bounded above by this first term, which is 1/3. So as you can see here, the sequence is bounded by below by 0 and bounded above by 1/3. So hence, the sequence is bounded. And then, finally, let's now apply the monotone convergence theorem to show that the given sequence is convergent. So the proof goes as follows. So by item number 1, the given sequence is decreasing and hence monotone. And furthermore, by item number 2, it is bounded. So hence, applying the monotone convergence theorem, we see that the given sequence is convergent. Okay, guys, so are there any questions, clarifications? So I will leave to you the following exercises for you to solve when you have free time. So thank you for listening.